Okay, part 3. Let's see if we can finish the rest of this. L'Hopitals rule is coming soon. Continuity. Continuity. Simply put, can I draw the picture without lifting up my pencil? But we have a better language for this. So a function is continuous at a point if, let's say a point C, it's point C, and if f of C is defined at x equals C, and if the limit as x approaches C from both sides is actually equal to the function at C, and that's continuity. And so we say a function is continuous everywhere if it is continuous at every point. You'll have my notes. So the question, so we saw like discontinuities. We saw that it might have been defined as C, but like you had to like lift up your pencil. Now either you lifted up your pencil because there was a hole, or there was a total jump. If it was just a hole, so there's discontinuity. It's removable if we can define f of C so that we can define. So we know that it exists. So for example, if we can define f of C. So for example, let's say we saw f of x equals x squared minus 4 over x minus 2. So we know what this looks like. We know it's a line. It's increased. We know at x equals 2, there's a hole in there. So you know what? Can I plug that hole in? Yeah. Just make this a piecewise function. And just say at x equals 2, it's 4. So now we've removed the discontinuity. We have for whatever reason, we wrote our function like this, and we removed the discontinuity by plugging the hole. When is this, therefore it's removable. When is it non-removable? Removable. It's not removable when the limit doesn't exist. When the limits from both sides, they're not equal. So for example, for example, f of x equals absolute value of x over x. There's nothing we can do to complete the curve. This is a jump. So it's like a jump. Jump. Okay, now let's get to the good stuff. Infinite limits. Let's see, can you see me? No. Next. Oh, you know what? Okay. Let's see. Let's see. Infinite limits. Now we're getting to the good stuff. Now, good. So, for example, specifically asymptotes. That's the point of this infinite. So, f of x equals 3 over x minus 2. Now, we've discussed this earlier on. We said, well, it doesn't exist, Mr. Eller, because it's unbounded. We know that the limit as x approaches 2 from the left side, it's negative infinity, or it decreases without bounds. And we know from the graph, the limit as x approaches 2 from the right goes to positive infinity, or it just comes out like that, and it's increasing without bounds. Now, it turns out, so we know, so therefore when we set the limit, it doesn't have a limit. A limit fails to exist because of the infinity or the unboundedness. But we can say that if the limit, if f of x, if as x approaches c from the left or the right, that f of x approaches positive or negative infinity, then what can we say? Then, now, x equals c is a vertical asymptote. Now we have a language for asymptote, a more mature, sophisticated language for asymptotes. The limit if the function is unbounded as it approaches an x value, we say that that x value is an asymptote. Right? And that's very straightforward. Next, so that's our vertical asymptotes. So it's very clear. Now let's get closer to some law. Let's move on. Well, we have the vertical asymptotes are very clear. The next thing is the horizontal asymptotes. Horizontal asymptotes. Because that's what we're interested in. As I said before, we're interested in approaching a point. You might say, well, Mr. Allen, like the equation y equals x, that just goes off to infinity. We're not interested in that. We want to know, we don't want behaviors as something gets close to something. So, let's move on. Let's move on to, I'm sorry. Good. Horizontal asymptotes. We're interested in the end behavior. End behavior of a function over an infinite interval. We're interested in what happens as x goes out to infinity. And we've seen cases like this constantly. The exponentials, the exponentials are like 1/2 to the x, it kind of like comes down. We say it's asymptotic to 0. We've seen this with the rational functions, where it's an asymptote to the x-axis, or like there's a line y equals 3. So let's examine this a little bit more. So let's look at f of x equals 3x squared over x squared plus 1. Now, the limit, so the question is, what's going on with this function as we go out to infinity? Well, as x goes to infinity, positive infinity, or negative, but let's check with the right side, this function approaches, let's bring that word back, approaches 3. Now, we can see this in the GDC. We can see this in the GDC. Now, so go back to your GDC, put this function in there, go open up a table, and then set the table, start at 0 and go up by like 10s or go up by 100, and you see the function goes quickly to 3. Now, because of rounding errors and decimals, it's going to say 3, but we know it's not getting there. That's rounding. If you go by 10s, you see like 2.9999999. You know what's going on. It's getting close. It's asymptotic to 3. So once again, we're looking at behavior. We are looking at behavior. Okay, so you're given these exercises, and you say, Mr. Adler, please show us we're getting the old school stuff. And then I will show you L'Hopital's rule, and you'll be like, this was a waste of my life. But it's not a waste of your life. Be patient. So find the asymptotes by hand. So you got the first function, f of x equals x cubed minus x squared plus 1 over x to the fourth plus 2x plus 5. Now, the old school way, and someone who's older might say, and they will say, and it's not wrong, but they'll say, first of all, find the term with the highest exponent. And you'll say, fine. Oh, I'm sorry, no. From by hand, I apologize. So find the limit. Okay. So find the asymptote by hand. Find the limit as x goes to infinity of x cubed minus x squared plus 1 over x to the fourth plus 2x plus 5. And the old school way is step 1, find the term with the highest exponent. So you're like x to the fourth. Next, divide everything by x fourth and rewrite the fraction. So you're like, fine, divide this by x to the fourth, 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 divide this by x to the fourth. Now, let's start over again. Okay, next thing we want to do is we want to find some asymptotes by hand. I know it's old school. I will tell you about lhopitals in a little bit. So the first thing, so how do we do it by hand? So find asymptotes by hand. And so the question is find the limit as x goes to infinity of x to the third minus x squared plus 1 over x to the fourth plus x squared, 2x plus 5. Now, some of you might be saying, Mr. Ruther, I know it's 0, because I can just see by inspection that the denominator is greater than there's the x to the fourth in the denominator, and it's clearly larger than the numerator. So, because the denominator is getting so much larger than the numerator, this is going to 0. True, it's not elegant, though. Let's be elegant by hand. So, step 1. You spoke about that x to the fourth. Find the term with the highest exponent and circle it, and divide every term by that x to the fourth. X to the fourth, 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 x to the fourth. Then what you're going to do is you're going to rewrite this fraction, but because of the limit rules, I can take the limit of the numerator and the denominator, and I can also take the limit of the individual terms. So I can write the limit as x approaches infinity of 1 over x minus the limit as x approaches infinity of 1 over x squared plus the limit as x approaches infinity of 1 over x to the fourth, all divided by the limit as x approaches infinity of 1 plus the limit as x approaches infinity of 2 over x to the third plus the limit as x approaches infinity of 5 over x to the fourth. Well, you know, this is now it's easy. You know that's 0, 0, 0, 1, 0, 0, answer 0. Let's try another one. Let's try another one. Y equals 3x squared plus 8x over 2x squared plus 5. So you might say, hey, Mr. Ruther, I know how to do this by inspection. I can look at that. I know exactly the answer is 3 over 2 because in the numerator and the denominator, the highest is x squared, and so it's like this race, and so it's 3 over 2. True, not elegant. So what do we do? Well, what did you mention? You said, oh, that x squared. So you know what? Divide everything. So I'm sorry. It's the limit as x goes to infinity. We're going to divide everything by the x squared. Divide everything by the x squared and say, fine. It's the limit as x goes to infinity of 3 plus the limit as x goes to infinity of 8 over x divided by the limit as x goes to infinity of 2 plus the limit as x goes to infinity over 5 over x squared. Sorry, I'm sloppy. You say this rather, that's great. This is 3, that's 0. This is 2, that's 0. The limit is 3 over 2. Should I give you another one? I'll write it down. The next one I was going to give you, you can skip over this. It was the limit as x goes to infinity of 5x to the 5th plus 2x plus 1 over x to the 3rd plus 2x squared minus 1. You know, you say, Mr. Adler, so you say, you know what, I'm not going to fight you anymore, Mr. Adler. I'm really tired. How are we doing for time? 15, we're almost there. We're almost there. We're getting there. Fine, let's just divide everything by x to the 5th. X to the 5th, x to the 5th. This ends up being like 5 over 0. Well, that makes sense because the greatest exponent was in the numerator. This is going off to infinity. It does not exist. Here's a challenge problem. What is the limit as x goes to infinity of 2 plus 3x over the square root of 3x squared plus 5? Well, it's not much of a challenge if you think about it. Think about it. Okay, here's the answer. Here's two ways of thinking about it. You can either go old school and rewrite this as the square root of 2x plus 3 squared over the square root of 3x squared plus 5, which is the square root of 4x squared plus 12x plus 9 over 3x squared plus 5. And therefore, the limit of this as x goes to infinity is equal to the square root of the limit as x goes to infinity of 4x squared plus 12x plus 9 over 3x squared plus 5. Right? Sorry, I'm running out of ink in my pens. I'm running out of ink. And therefore, it's equal to what? The square root of 4 over 3, which is 2 over radical 3. And you should say, oh, you know what? I could have just taken this and this off. That makes sense because as x gets ridiculously large, this 3 and this 5 don't really matter. So this actually becomes 2x over the square root of 3x squared, which becomes 2x over radical 3x. That's where that comes from. Okay. Let's keep going. The next thing we want to talk about the penultimate topic, differentiability. Simply put, a point is differentiable if in the neighborhood around it, every point is differentiable. Here's how I would describe it, and you're not going to be asked about it on the IB exam, but this is the idea. My metaphor for differentiability was the tangent line, right? And simply put, pick a point, any point on your curve. Imagine there's two surfboards coming up the curve from the left and the right. If the surfboard from the left is the same thing as the surfboard from the right, or let me use different colors, So, imagine this is red, sorry. Okay, left. Okay, let's talk about differentiability. My battery all right? No, I'm good. Differentiability. Okay, here's my metaphor for it. We'll keep it very simple. Imagine there's a curve. Okay. Now, the metaphor I've been using for tangent lines is surfboards. Okay. What I want you to imagine is if you're going to pick a point, and the question is the function differentiable at the point? So you pick this point over here. I want you to imagine there's a surfboard on the left, and I want you to imagine there's a surfboard coming up on the right. If the surfboard from the right, if the surfboard from the left at that point is the same thing as the surfboard coming from the right, that the function is differentiable at that point. That's the definition of why a point is differentiable. Now you might ask, when is a point not differentiable? Well, let's take a look at the graph of y equals absolute value of x. Okay? If we take a look at the graph of absolute value of x, we have, well, let me use my green and blue metaphor. Here's my red surfboard from the left. Here's my green surfboards from the right. What happens when they get to 0? What's going on here? What surfboard do I use? The red, which has a slope of -1, or green, which has whose surfboards have a slope of 1? Well, because it's different, or there's two different ones, it's not differentiable. It may be continuous. It may be continuous, but it's not differentiable. So you can say that, and you don't need to know this for this class, you'll need it for college, but differentiability implies continuity, but continuity does not imply differentiability. Just because you don't have to lift your pencil doesn't mean I can find the tangent line at every point. Another example is y equals like x to the 2/3. And this curve kind of looks like this. It's kind of like a, what is it? It goes up like that and it goes like down like that. No, I'm sorry. No. I apologize. Here's one. X to the 3, it looks like this. And it's the same idea. The surfboards are coming at it. Now, what's happening here is that the surfboards are actually not even defined at 0. So once again, this curve is continuous, but it's not differentiable everywhere. Okay. Now, and once again, I'm not even going to ask you questions on it. IB is not asking you questions on it. Okay. Now, L'Hopital's rule. Now we're ready for L'Hopital's rule. It's very simple and very basic. It's simply L'Hopital's rule says, ready? L'Hopital's rule. L'Hopital's rule. It's very basic. After substitution, if the limit as x approaches a is equal to 0 over 0, or the limit as x approaches infinity, it ends up being infinity over infinity. For this class, it has to have these two forms. Then it turns out, are you ready for this? It turns out the limit as x approaches either your 0 or your infinity of f of x over g of x is actually equal to the limit of the derivative of the numerator over the derivative of the denominator. Simply put, if you get 0 over 0 or you get infinity over infinity, just take the derivative. That's it. That's it. So, like, the limit as x goes to infinity of 5x squared plus 2x over 6x cubed plus 10, you visually see this as infinity over infinity, right? Well, just take the derivative. 10x plus 2 over 18x squared. Once again, take the derivative. Infinity over infinity, take the derivative over again. You have 10x over 36x. Okay, now we're at the final place. L'Hopital's rule. L'Hopital's rule. It's very basic. The idea is we have plenty of examples. Simply put, you're going to substitute. After substitution, if the limit as x approaches a of f of x is equal to 0 over 0, or the limit as x approaches infinity of f of x is equal to infinity over infinity, right? This is cool. It turns out there's a rule. Just take the derivative of the numerator and the denominator and resubstitute. In terms of the limit as x approaches a or x approaches infinity of f of x over g of x is simply equal to f of prime of x, the limit as x approaches a or x approaches infinity of the derivatives. And keep taking the derivatives until you get something that you recognize. Once again, it always has to be in the form of 0 over 0 or infinity over infinity. Let's take an example. What is the limit as x goes to infinity of 5x squared plus 2x over 6x cubed plus 10? So you say, well, Mr. Allen, we don't want to do that anymore. You don't. L'Hopital's rule says, you should look at this. You say, oh, it's infinity over infinity. Do I have to do that thing you made us do before? No. L'Hopital's rule says this is equal to the limit as x goes to infinity of 10x plus 2 over 18x squared. Mr. Allen, I have an infinity over infinity again. Use L'Hopital's rule. This says that the limit as x goes to infinity of 10 over 18x is equal to 10 over 18x. You say, oh, you know what, Mr. Adler? I know this. That's 10 over 18 times the limit as x goes to infinity of 1 over x. That equals 0. Done. And you can see that all those problems we did before. You can take the derivatives. This first problem is just like that problem. And the second problem we did is just like the first problem. Well, let's go through the whole course, what we did. Let's go through a couple of these. Let's just literally go through every single problem we did. How about, what is the limit as x goes to 0 of sine of x over x? Well, you say, okay, you know what, Mr. Adler? Well, that's 0 over 0. Do I have to do that whole 16-minute lecture you gave us? No. What does L'Hopital's rule say? This is equal to the limit as x goes to 0. What's the derivative of sine of x? Cosine of x. What's the derivative of x? 1. Substitute, answer 1. Sorry. Let's try the first problem I gave you. What's the limit as x goes to 0 of 2 to the x minus 1 over x? Oh, look, Mr. Aller, when I substitute this in, I get 0 over 0. So do I have to, go to my calculator? No, L'Hopital's rule. What is the derivative of 2 to the x? It's 2 to the x, 2 to the x ln of 2 over 1. Well, when I plug 0 in, I get the answer, ln of 2, which is approximately 0.693. Let's try another one that I made you. Let's go back. Let's find, another problem. Okay, let's try perfect. What is the limit as x approaches 1 of x cubed minus 1 over x minus 1? Oh, Mr. Adler, I think there's a whole, should I factor x cubed minus 1 and then cancel out the x minus 1? No, because it's 0 over 0. L'Hopital's rule. This is equal to the limit as x approaches 1 of what? 3x squared over 1. When I plug the 1 in there, what's the answer? 3. Let's try another one that I gave you to do. Find the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. I remember this, Mr. Do I have to rationalize everything? No, L'Hopital's rule. Because 0 minus 1 minus 1 is 0 over 0. 0 over 0, L'Hopital's rule. The answer was a half. Well, do we got that? Let's see. This is 1/2 x plus 1 to the negative 1/2 over 1. Well, 0 plug the 0 in, 0 plus 1, anything to 1 to any power is 1. Sorry. Let's try another one. The last one. Oh, let's go back to the squeeze theorem. Let's go back to the squeeze theorem when I made you do that cosine. That'll be the last one. Let's look at that cosine. How about a cosine h minus 1 over h? The limit as h approached 0. So, Mr. Adler, do I have to do like that, multiply top and bottom by cosine plus 1 over, no, L'Hopital's rule, because you have the cosine of 0 is 1, 1 minus 1 is 0, 0 over 0, I can use L'Hopital's rule. What's the derivative of cosine? Well, it's negative sine of h, and then the derivative of h is 1. Well, what's the sine of 0? 0. That's it. So, study all the limits, go over the problems, but please remember, if you have 0 over, first of all, try to substitute. If you get a nice number, you found the limit. If you get 0 over 0, use L'Hopital's rule. If you get infinity over infinity, use L'Hopital's rule. That's it. Thank you for listening.